the things that we do are like based heavily on rather complicated mathematical definitions, and some of this stuff you almost have to take on faith at first. But I'm going to try to hit everything, do everything that I need to do to show you how this stuff works. And we're going to be talking about these things. Like when you talk about the E field, for instance, well, it's invisible, you don't see it. We know it's there because we can measure it. The E field itself is a vector. And it also is something that has, the units are volts per meter. The only way we can find out what the E field value is if we put up something, effectively a charge, that it can actually strike and press a force on. But the E field, nevertheless, is important to understand. So is the B field. So anyway, this is from scratch. The two laws that I gave you, just have to accept these. I mean, the two curl equations. Curl of H is equal to J plus the partial of D with respect to T. And the curl of E equal to minus dB dt. These are kind of fundamental. Those are Maxwell's equations, and they're based on experimental evidence, lots of experimental evidence. The things that link these things, D we know is epsilon E, and B is mu H. So that's for sure. Now, after that, what we can do is take this equation and simply expand it as J plus epsilon times dE dt here. And the only thing I've done here is replace D by epsilon E. And then I'm going to add another one that you should know. This is the differential form of Gauss's law. It's the divergence of D is equal to rho V. And because D is epsilon E, its divergence of E is equal to rho V over epsilon. Now those are laws that you've seen before, you've applied them. J has to do with the real current, really, and I'm going to go ahead and make this minus mu times, no, actually, I'm going to leave that alone. I'll leave that alone right now. All right, so those are the laws that you're familiar with. These are vector field equations. This is a scalar equation. Now here's the new stuff. Now we talk about a magnetic vector potential A. And A is something defined as really mu over 4 pi. I mean, I should say if I have a differential chunk of current I'll put it in the Z direction. But this is the wayest this board's ever looked. If we have I here, and it's in the AZ direction, so this is the Z direction, so it's IAZ right here times DZ, and DZ would be the thickness. Then if I come out a distance R from here, I can say that this value of the differential value of AZ here would be equal to mu 0 over 4 pi, and then it's going to be times I, and it will be that I, but there's the thing that happens here, because there's a time delay. Normally they would put, I'm just going to write this once, I of t minus r over c, because it would be speed of light time delay here, and I can make this I a function of t as well. Y'all follow me what I'm doing here? And then this is divided by r, and it would be in the AZ direction. And then it's times dz times AZ. It has to have the differential height. So try to appreciate one thing. This magnetic vector potential, I'm showing you here is the differential magnetic vector potential, is mu I, and then it's the value of I with a time delay of t, which is really capital R over c. That's speed of light time delay. I hope you can appreciate this. Times dz az. This doesn't mean much to you right now, but here's the beauty of this. This differential vector field right here is only in one direction. It's in the direction of the current element causing it. And this becomes important in a bit. Now the next thing I do, not bad, is now I'm going to make a couple of points. You know how we can work in the time domain or the frequency domain, right? We're going to work in the frequency domain. And that means this I here, I of t, is really the real part of I phasor Well, it's a vector phasor times e to the j omega t. Now what that does for me is because I've got e to the j omega t here, when I put e to the j omega t here and take the real part, what this breaks down to, I should do this one time, but I'm going to leave it like this for now, is simply I naught, whatever the value of I naught here is, e to the minus j beta r. It's just a phase difference. And the reason it's the case is normally you're used to seeing cosine of omega t times I naught. That would be a current. Do you agree with me? Well, if you put the time delay in there, then it would be I naught times cosine of omega times quantity t minus r over c, or I naught times cosine of omega t minus omega r over c. And omega over c is beta. Y'all follow me there, class? Right here, this quantity, omega over c, when I put in t minus r over c, which is the time delay for how fast light travels, or electromagnetic energy travels, then you would have omega over c times r, which is beta. And so you can write this as simply beta r. Beta r. And then, if this is I of t, you can see that this I of t is really expressed as the real part of the phasor I, which would be I naught right here times e to the minus j, or plus j omega t times e to the minus j of beta r. And the real part of that would be the cosine. So, this is the phasor form. Just leave it at that for now, and you'll see where I'm going. Now, here comes the vector, the buildup of the vectors. And this, by the way, will become a little more clear in time. Anyway, we're going to use these vectors, this magnetic vector potential, to create or to define both the E field and the B field. Now, the thing about a vector, you have to understand, if its curl and its divergence are defined, it is uniquely defined. It can't be more than one value. For instance, if you just define the divergence of a vector, divergence of A is something, well, you're going to have the behavior of A, the divergence is derivatives, right? So you can have the slopes and the curves, how it varies through space, but you don't have the absolute value because you don't have that constant C. But when you define the curl and the divergence of any vector, you uniquely define the vector. One and only one vector can solve that. Follow me? So here's what we do. And I'll show you how it works. We're going to say that B will be defined as the curl of A. And we're going to define E. Now before E was minus the gradient of the voltage. But now it's going to be minus the gradient of the voltage minus dA dt. So now, what I'm doing is I'm defining the curl of A, and in a second I'm going to define the divergence of A based on this. Are you with me? Remember, A is a unique vector that you have not seen before. You've seen voltage, you've seen the potential, right? But you have not seen A. It's a magnetic vector potential. And the curl of it defines B, and now we're going to find out the divergences of this. So here's how this works. Do y'all remember with Maxwell's equations, this is like one of the go-to equations. That's Gauss's law. Actually, it's not Maxwell's equations, but it's Gauss's law in the point form. Do y'all remember that? Div D is equal to rho V. How many remember that, by the way? The point form of Gauss's law, it's important. The integral form is the integral of D dot ds is all the charge enclosed in a region. The point form is more useful sometimes. But we use this law and we apply this equation. So we take the divergence of E, which is now divergence of E is equal to the divergence of minus the gradient of V minus dA dt. And we set that equal to rho V over epsilon, or just over epsilon. You follow me so far? Now keep watching. Now when I do this, I get, well, the divergence of a gradient is a Laplacian. The symbol is minus del squared of V minus d dt of the divergence of A is equal to rho V over epsilon. over epsilon. You with me so far? You don't even need this one. And what's usually done at this point, you take the minus sign and put it on this side of the equation. Make that plus. Follow? We're not there yet, but at least you see I've got divergence of A defined. I've defined the curl. There's the divergence of A. Correct, class? I won't expect you to reproduce this. I just want you to appreciate it as much as you can. Next, I come from here, and I say that also, I know that the curl of H is equal to J plus the partial with respect to D of T. And actually, I'm gonna forego that step. I'm just gonna put epsilon times dE dt. You all agree with me there? Right? That's basically Ampere's law, is it? Everybody? Now keep watching. Instead of H, well, if I define B as curl of H, then H would be equal to 1 over mu times curl of A. Do you all agree with me there? Because B is mu H, agree? Now I can come over here and I can say, therefore, this becomes 1 over mu curl of A. And I've gone ahead and I've taken that H and stuck it right there, so I get two curls right here. And that equals J plus epsilon times dE dt. Well, what is E? It's this. So it's the partial with respect to ddt of minus the gradient of V minus dA dt. I know this looks mathematically clumsy. Right? When I did my PhD, it was a nonlinear transient, well, actually it was linear transient electromagnetic modeling of charge perturbations related to lightning. Really, my thoughts were it was more along the lines of what happens to the atmosphere's response to electromagnetic perturbations and charge perturbations due to nuclear weapons, but forego that for now. It was really about the electric field signatures from lightning, and they actually, things that were predicted by this code we developed were observed. But in order to develop the code, I had to be really familiar with Maxwell's equations. And I'm messing around with these all the time, trying to cast them in a form that are solvable. So, and it was a simulation, it wasn't an empirical model where you just had a closed form solution. So for this time, if you look, what we're going to do is multiply both sides by mu. So I'm just going to take that and multiply mu there. Then the next thing I do is a vector identity. I don't know if anybody remembers this one, but curl of a vector is the gradient of the divergence of that vector minus del squared, the Laplacian of that vector. And that's equal to mu times J plus epsilon times mu. And then it's going to be times, I'm going to do it this way, minus the gradient, no, I can't do it, I'll do it this way, it'll be, minus the gradient of dV dt, that's a legal operation, and then it's going to be minus the second derivative of A with respect to t squared. You all see what I've done here, I've taken the gradient from V and I put it outside and I took the time derivative inside. That's a legal operation. Time and space derivatives can be interchanged, unless the spatial component is a function of the actual time. And I'm not going to get it, that's nonlinear, but y'all follow me what I've done so far? Now, just hang on, you will in a second. Now, here's what I'm going to do. There's a divergence of A there, right? I've got a voltage here. So what I'm going to do is say this. I'm going to equate this to that. So I'm going to say gradient of the divergence of A, just write this down and keep watching, is equal to minus mu epsilon times the gradient of dV dt. This is an important step. Now I'll take everything to one side and I have basically this. I have the gradient of the quantity divergence of A plus epsilon mu times dV dt. Remember, that's a gradient operator, is equal to 0. And I can do that. So I'm saying this is going to be equal to this right here. Are you with me? Now I've uniquely defined the divergence plus epsilon, or epsilon mu times dv dt. And this is called the gauge condition. Have you heard of that in physics? When you say gauge, it really is this. You're saying you're going to define what a constant in an equation is that's buried in the equation. So I'm going to say that now divergence of A plus epsilon mu dv dt is equal to 0. And this is called the Lorentz gauge. Right here. There's also something called the Coulomb gauge. It's only something that nails, obviously now the divergence of A is set in terms of voltage, right? You can take that to the other side. So now both the divergence and the curl of A are uniquely defined. But that does a few other things for us. And I'm going to need a little more of the board. I'll try to do it right here, if you'll bear with me. So now, when I come back here, remember I set this equal to that. What does that mean? It means this plus this plus this. This equals this plus this. Now watch. So if I take this right here, first, I can forget about that, and I can forget about that. I equated those two. The sum of those two was 0. Do you all recall that? Yeah. All right, so now I'm left with this. I have minus del squared of A here. And then I have equal to mu times J, and then minus the mu epsilon times the second derivative of A with respect to T squared. Just bear with me. This is real important. So now I'm going to multiply through by a minus sign, both sides, and I'll take that to this side. And then I'm going to get this. Del squared of A, all right, it's going to be that minus mu epsilon times the second derivative of A with respect to T squared is equal to minus mu J. Block that right there. And I'm going to write this one right under it. Del squared of V, wait a second. Yeah, del squared of, I'll just do it this way. Take a look at this now. For A, I'm going to put in A is equal to minus epsilon mu dv dt in that equation. So now I get del squared of V minus mu epsilon times the second derivative of V with respect to T squared is equal to minus rho V over epsilon. Both of these equations are called, they typically are called a Helmholtz or wave equation. Or wave equation. And I'm going to make mention of a few things. If we're dealing with something that's not time varying, this would go away, wouldn't it? And I'd have del squared of V is equal to minus rho V over epsilon naught. Do you all remember that from electrostatics? That the del squared of the potential is equal to minus the charge density over epsilon? How many do? You remember a little bit? You all remember this right here? Gauss's law, div D is equal to rho V. You all remember that? You all remember that div E is rho V over epsilon? Because that's just simply what? Defining D in terms of E, right? And you remember this, that when you had electrostatics, E was equal to minus the gradient of the voltage, correct? Y'all remember that? Well, if you remember that, well, if you put this in here, I get the divergence of minus the gradient of V is equal to rho V over epsilon. The divergence of a gradient operator is by definition del squared, and this becomes del squared of V is equal to minus rho V over epsilon. You follow me? Now, my point is, that's electrostatics. Here's the complete equations. It's time varying. If there's no time derivative, it reduces to the electrostatic equation for del squared. Follow me, class? The way you actually solve the del squared V is equal to minus rho V over epsilon, this one was by using what? You wrote the differential equation down, you found the general solution, then you used boundary conditions to find the exact solution. Does anybody remember doing that in EMAG 1? Kind of, sort of? You did it in physics too. You probably don't remember that part, or you should have. So now we have these two equations. Well, now the obvious question is, how does that help me with antenna theory? So now I'm going to get to that. But I want to at least set you up. Those are the equations we want. And I'm going to get back to this in 1 second. Now, come over here, and I say that if I have a current in the z direction, call this the z-axis, and this current is I naught dl, but it's also, it's time varying, so it's a phase, it's got that e to the minus j beta term that's going to appear, and this is going to be at the origin. Let's say it's at the origin right here. And I come out at distance, it doesn't have to be at the origin, distance r away. Now I can say that my differential A vector, right here, the differential magnetic vector potential is equal to simply mu over 4 pi divided by r, and it's going to be times I naught e to the minus j beta r, and it's going to have the dz in it because I have dl, but the height here is going to be dz, so it's the differential length has to be in there. And it's in the az direction. Now that's it. That's a differential form of A. Now how does A give me E? That's the question. And forget about differential or not. You can, I don't have it down there, but the E field is generally given as minus the gradient of V minus dA dt, right? That I said. Now we're going to go into the phasor domain, so time derivatives pull out a j omega, correct class? So now I say that E is equal to minus the gradient of the potential minus, and then it's going to be j omega times A, right there. And this is true generally. Now I have to tell you this, so we're not going to do this part, but you have to understand something. If you have a chunk of current moving up, suppose this is a short antenna. Whenever current moves, there's automatically going to be plus charge and minus charge accumulated. You follow me on that at the ends? It's an impossibility. Charge doesn't disintegrate to another dimension. If you have a small chunk of current, let's say we have a small antenna there, then charge, if you're moving current up, it's going to accumulate positive here and it will have negative there. Do you follow me? That plus and minus charge will give rise to this. I'm not going to calculate, I'm just mentioning it. Charge is associated with the potential volts. Do you follow me? A is associated with the current. But here's the one beautiful thing. If you're in spherical coordinates that happens, and please listen to me here. I want to draw this bigger and I want to do it right here. If you have a differential current where this is going to be I dz in the AZ direction right here, and you're a distance r away from that, your A field, here, your differential A field here, would be equal to I times mu over 4 pi I naught times e to the minus j beta r in the AZ direction. But if you want to calculate the E field from that, if you go ahead and calculate this clumps of charge and the V from it, do the gradient operator and everything else, you'll find out that the E field, this would be the E field, and it would be in the phi direction. All right? You know that phi is this, A phi is a direction that is perpendicular to R, but it's pointing like from the North Pole to the South Pole over the radius arc. Do you all remember that class? A phi? A theta, pardon me, A theta. So you can get this, and it's equal to simply minus this differential, this would be the differential E field, pardon me. Differential E field would be equal to this right here, DAZ, the differential field in the Z direction, and it's just times, I gotta do this, I gotta explain something. You see how it's minus j omega A, right? It will be equal to minus j omega AZ, and here's the thing I'm going to try to just mention. The gradient operator here, related to charge, basically influences the actual orientation of the E field, so the E field is always going to be perpendicular to the R vector. You follow me on that, class? Now, you're going to wonder, how can that happen? Well, try to understand this. When I have A, it's only in the Z direction, right? Correct? If I look at the actual, how these charges would affect the value here, if I have plus charge, it would, let me go up here. If I have plus charge, it actually pushes this way. Negative charge would pull this way, and the net value of that field would be like that, if you follow me. You could do this triangulate. Well, what that does, when you add that to this, is bend it just enough so it's going to be minus j omega times AZ, and then it's going to be times the sine of theta. And this is DAZ, by the way. Now, this is not when Dr. Wentworth spoke, but I'm trying to, without getting into very complicated mathematics, I'm trying to make this at least something you can appreciate. Now, if you look at this is the differential E field from a differential length of charge. And AZ here has the differential length, or should at least, should have DZ in it. Let me go ahead and do this. I'm going to say that therefore dE theta in the theta direction is equal to minus j omega, and then it's going to be mu times I naught e to the minus j beta r, and it's dz az, write this down, over 4 pi r, and then it's going to be this times the sine of theta. So it's minus j omega mu I naught e to the minus j beta r, dz, which is the differential length sine theta over 4 pi r. And it's really, if you want the differential E field, if you want to make that a vector, then you would just put a theta here. Now, that is real important. This is one you write down. This is the differential electric field from a differential current element in the Z direction. Do you follow me, class? I'm going to show you what he has in his book in 1 second. So, and I'm going to tell you, you can get that if you want to do the math on this. Here's one thing you can do. I'm just going to say this. I don't want to go through this part. Remember, we had the differential value for AZ right here, didn't we? Now watch. Here's what you can do. You can get the differential B field, because B is equal to curl A, is equal to the curl of the differential A vector, right? And once you have the differential B field right there, all right, that's equal to mu times the differential H field. Follow me? Then what you can do is say, well, I know that the curl of H is equal to J plus, and then it would be in the phasor domain J omega epsilon E, right? Now here's the thing. If you're not at the source, if you're away from the source, this goes away. So I have J omega that's an epsilon here, not a Z, epsilon E. Well, I have curl of H, and if it's a differential, then it would be curl of DH, which would be this. This would be 1 over mu curl of this, dA, right here, would be equal to that, and then you would divide this by J omega mu epsilon, and you would get E, and that curl equation is what is expanded right here. To make a long story short, once you take curl of A, then you have to take it again. You have to take curl of H, DH, to get the E field. And that's more involved. It drives you nuts, is what it is. It's a bunch of curls in spherical coordinates. Understand, class? I didn't want you to do that. The net result after you do that is this. All right. So here's the upshot of the whole thing. If you have a small piece of current on the z-axis that has a length dz and has a value, a magnitude of I naught, and it's a sinusoidal, it's really a time harmonic current, which means that it's sinusoidally or cosinusoidally varying, then this is in fact the value of the E field you get. And it's in the it's in the A theta direction. Okay? I'm going to mention one thing about this. This is the propagating electromagnetic field. It's the field that's going to be launched from an antenna. And I've got to make mention of this. Now, I think I might have said this before, but I'm not sure. When you deal with just a capacitor, right, you have basically a piece of insulator separating two plates that accumulate charge, plus and minus charge. The net sum of the charge in a capacitor is always zero, isn't it, class? But when you have a capacitor, anywhere about that capacitor, you have an electric field, either between the plates or something we call a fringing field that's around it, right, class? You all remember that? Now, that electromagnetic energy is not propagated. It's static, isn't it? If you charge a capacitor, the electrostatic fields about that capacitor are there. They're not launched into deep space. Even though you might say it's mapped into space around there, they're not leaving the thing, right? So if I put a resistor across that capacitor, all that energy in the electrostatic field shorts out and then it discharges through the resistor, and you would short out the cap. Does everybody agree with me there? That energy is resident. If you have an inductor, a bunch of coils of wire with a current, well, if there's current flowing in there, there's magnetic energy in the near field, causes a magnetic field, right? The magnetic energy density is 1/2 mu h squared per volume. It'd be in really joules per meter cubed. And it's about there. But if you take that, you've got that much current going through an inductor. If you take that and then put a resistor right on the ends of the inductor, all that magnetic energy would be deposited in the resistor. Do you follow me? That means both the electrostatic and magnetostatic energy are not launched. And it's because there's no acceleration of charge, and that's the key to this. Anytime you have charge acceleration, you launch electromagnetic energy. You create photons and they're launched. This is more physics than you need for today, but when we're talking about an antenna, what it effectively does is take current and create photons that are launched. They're never coming back. When you have an electromagnetic wave that's propagating, it's never coming back. This is what we're talking about here. This is an electric field that is not related to the electrostatic charge or the magnetic static current. It is launched for good. Do you follow me, class? Now, there is about an antenna or any kind of chunk, there is an electrostatic field that we'll talk about, and there is necessarily a magnetostatic. But those are not terms we're really interested in because that is local to the antenna and that energy can be collapsed back into the antenna. We're worried and focusing on things that are launched. And this is far field. That's things that go into the far field. And I'm just making mention of that. So now that I've said all that and spent some time doing this is the real way it's shown. Now what I can do is this. Leave that up here. And I'm going to show you how his equations are created from this. Because his stuff is really based on a lot of stuff where he's trying to use some of his integral equations that define B field from current density and stuff. And honestly, I'm sure I don't appreciate it the way he does, but it doesn't really do it for me. This does. Now watch this. This is important. Dr. Wentworth doesn't have this formula. He has one close to it. He doesn't use DZ, he uses DL. So you can put L in there if you want. But it's effectively Z. I prefer Z myself. Now here's where there's a difference. If you look at this term right here, mu omega. I want you to follow me on this. Omega mu. Let's see something. Instead of that, he has eta beta in his book. He says this is equal to eta times beta. Let's see if it is. what is eta equal to in a lossless region? Does anybody remember? In free space, what is the intrinsic impedance of free space in terms of mu and epsilon? Anybody? That's right, square root of mu over epsilon. Now, what is beta in terms of the intrinsic parameters, mu and epsilon? Beta now.
Omega squared.
Not omega squared, just omega square root of mu epsilon.
Squared.
Right? Isn't it? Omega times square root of mu epsilon? I know a lot of this, there's just a lot of symbols. Well, go ahead and multiply this through. What do you see happening? That cancels, and that becomes omega mu. Do you all see this, class? Therefore, this equals this. Now, Dr. Whitmore's book will have this formula. He'll have dE, and this is for a differential length of current on the z-axis, centered at the z-axis, as a matter of fact. He has I naught here of length dl or dz, and he comes out, and this is theta measured from the z-axis. He comes out and he's talking about this E field, E theta, and he says E theta here is equal to minus J, and then he'll have eta beta times I naught, and then he'll have times dl, or L, I think dl, over 4 pi r. Then he'll have the sine of theta times A theta. You all see that in his book? Now, I think he has differential. He might have E. Does he have differential or does he have E?
He just has E.
Okay. It doesn't matter. The reason I say differential, if he doesn't have the differential there, then he has L here. But this is going to be for L much less than lambda, wavelength, in free space. Put that down too. And this is Dr. Whitmore's book. The two are identical. Now, the next thing I'm going to tell you is that if we have the magnetic vector potential, we could get the B field by taking the curl of it. Do you all agree with that? I define curl of A equal to, curl of A is B, right? Right? And if we have B, we have H. We could do that. And in Whitmore's book, he does do that. But I'm going to say that this is such a nice thing to know. If we're in the far field, and write that down, far field, something happens. Far field means, there's a lot of definitions to it, but here's the one that works all the time. I'm away from I'm far enough away so that the electrostatic energy or magnetostatic energy does not, the magnetic fields or electric fields due to the static or to the DC currents are now of no consequence. I'm far enough away. And you don't need to get very far. So now, if I'm in the far field, this is where all the energy is launched at that point. I'll get down to the specific definitions of how far you have to be for the far field in a bit. But for now, I'll just put down far field. If you're in the far field, then I can tell you that E cross H is actually the pointing vector, what I call S, the power flow. And Dr. Whitmore's book, he calls it P Av, the power flow, E cross H. And really, why don't I put I don't want to put the time domain form. It's actually 1/2 times the real part of E cross H conjugated. Do y'all remember that? And here's another thing. E cross H divided by the magnitude of E cross H is always a vector pointing in the direction of propagation. AP is a unit vector in the direction of propagation. You remember that from before? Now this is important. If you have E, you can find the direction of H because E cross H is radially outward. Things are launched in the radial direction. It also means this, too, that the ratio of the electric field over the magnetic field, and this is all in the far field now, the magnitudes of this are equal to eta in the region. So, because of that, I can do something really nice. If I have the E field, if I want the H field, I can say the H field, all right, will be perpendicular to this and perpendicular to the direction of propagation. Well, if E's in the theta direction, right, and it's propagating in the R direction. It's launched out, right? It's leaving. Well, E cross H has to be the direction of propagation, and therefore H has to be in the phi direction. If E's this way, H has to be phi, and that would be H would therefore be, or I'll put down H phi right here, would just be equal to E, the magnitude of that, would be E theta divided by eta, and it would be in the A phi direction, or specifically it would be minus J times beta times I naught times L over 4 pi R. Then it would be sine of theta, and it would be A phi, and that would be H. Do you see that in this book for far field H? Class? What page is that on?
443. Yeah.
443, what equation?
849. Yeah.
All right, now that's far field, remember, and that's what I'm focused on. We'll get to near field stuff in a bit, but stick to far field. Now, if I have that, the next, this is a short dipole, by the way, and I'm just going to say that what I've done there, even though it was infinitesimal at first, if I make this stipulation that the length has to be much, much than lambda naught, and it's lying on the z-axis, they term this a Hertzian dipole. Or a short dipole. I personally like the term short dipole. That's how it's always been. Hertz gives too much credit to a person. It's not a rental car agency either. It's Henry Hertz. Yeah.
In the book for the H field, it doesn't have negative J, it just has J. And it's the same for the E field.
There's also E to the J beta term.
Oh yeah, it has to be E to the beta J beta. Minus J beta R.
Minus J beta.
It should be E, sorry, E to the minus J beta R. Oh, you know what? You're right. Here's why. When I put E is equal to minus the gradient of the voltage minus the ADT, right? When I do this, this is going to be minus the gradient of V minus, and this becomes minus J omega times AZ vector. But remember, AZ is pointed this way, E theta is pointed this way, and the vector, what you're really doing is this, and I don't mean to say or get off track here, try to just appreciate one thing. If this is I dl here, and I'm a distance r away, and my vector is this way, this is AZ. The way it's normally done is you take the projection of this vector perpendicular to the actual r direction. So that would be this, which is going to be the sine of that angle, this angle right here. All right? Now, that direction right there is minus, that's AZ, and then it's got the minus J omega term. Well, sorry, this is when this plops down to, that's what I forgot the minus there. So this will become J omega times AZ, and that's positive, times the sine of theta in the A theta direction, and that will be the E field. I'm sorry, it is positive. You go through the entire curl. If you calculate what A is, then take the curl of A to get B, divide that by mu. Now you have H, and take the curl of H again, then you will get J omega epsilon times E, and then you divide by J omega epsilon. And the J's basically get rid of that negative sense, but I really don't want to do this. This right here is right, and it should be a positive. You're right. I'm sorry about that. All right. Now, he has this in his book. This is in the far field. Let me show you a few things now that are important. First, the relationship. If you have the E field in the far field and you want the H field, you just divide by eta and find the direction. E cross H is in the direction of power propagation. The next thing we have to do, and these are things that are fairly important. we have to find the power density and then the total power radiated. So that's the next thing I'm up to over here. And you know, I'm not too old to remember when I was in your shoes, a lot of this stuff seems really far away from abstract. You don't see the practical application of it, but you will. Remember these two equations for short pieces of wire with current. By short, I mean electrically short, much less than a wavelength of current in it. This, believe it or not, this really is applicable to a large class of simple antenna systems. You know your cell phones? Back in the day when you had just a straight wire antennas, does anybody remember when you pulled up the wire? Those are aerials. Those are simple short dipoles. They're not half-wave dipoles or anything like this. This applies to it, this theory. So now, the next thing we need is going to be, y'all have these written down? Okay. It's in your book too. It's going to be calculating things like power density from that, and then the total power, which is important, flowing from the antenna. Because from that, we can get the resistance. Remember, when you have a piece of wire and you're putting current in it, right? A current that's going to have a time, it's going to be really a time harmonic, a cosine of omega t kind of variation. You have charge accelerating. Whenever you have charge accelerating, you launch photons, right? Well, that's energy being launched. It doesn't come from nowhere. So that means the energy has to come from the current providing it, which basically gives you an internal antenna, or an internal a resistance, a true resistance of that piece of wire that would not be there at DC. You follow me? This is going to be only when you have an acceleration of charge, you get what we're going to look at. So first, we get the power density. I like the term S because it's actually more commonly used, and it's the pointing vector, which is actually what he calls PAV in his book. And that's equal to 1/2 times, really the real part, of E cross H conjugated, right? Now, I told you before when we were talking about plane noise, does anybody remember if you're in a lossless media, how we can calculate that? Anybody? Well, let's assume that we're going to talk about this only for the short dipole. So now we're going to limit ourselves to the short dipole. And we've got a current, this is DZ, or I'll just call it L. And I'll make sure L is much less than lambda. I have a current here of I naught. I'm coming out a distance R away. And now I want to know either S or PAV out here. Do you remember how I get this? Well, what coordinates system are we in? Spherical coordinates, right? Which way is power propagating? If the source is at the origin, it's propagating in the radial direction, right? In the R direction, correct? Well, I know the direction. It's AR. I mean, does this make sense to everybody? What I'm doing here? It's a little casual in terms of exactness, but I'm trying to just communicate the ideas, the concepts. It's not going anywhere but away from the antenna. Do you all agree? If the antenna's at the origin, it's got to be going in the radial direction without too much ado. All right, now what's the magnitude? Do you remember what the magnitude is for power density for a plane wave in free space? Does anybody? Or in space? Power density. How many remember it's just given as 1/2 magnitude of the E field squared over eta? Remember that or not? How many do? E is like voltage, eta is like resistance. Think about it, back in the day when you had power, right? AC power, 1/2 the magnitude of V squared, V being the maximum value of V squared, divided by the resistance was the power, wasn't it? Same form here. Now you can do this, and he does it in his book just to show you it works. Where you go ahead and take the E field and cross it into the H field conjugated, and lo and behold, you're going to get what I'm about to show you, but it's easier this way, in my opinion, all right? So here, remember what the E field was. I know you're new at this, but this is J, from this condition, it's J eta beta over 4 pi R. Here, it's going to have I and DL, I naught DL, or I naught L actually, in his book he uses L. So it's going to be I naught times L. Then he has e to the minus j beta r. And then the sine of theta. And it's in the a theta direction. That's his E field, I believe, if you look at the book. Right?
Yes.
Now, if you take, I want the magnitude squared. If I just take the magnitude of the E field, you'll notice I get rid of the J, don't I? And I get rid of this e to the minus j beta r, because that's only a phase angle. And I get rid of this. Does everybody agree with me there? Now, if I take this and I square it, right? If I take, and I'll put it right here, magnitude of the E field squared, now that's equal to eta squared, beta squared, I naught squared, L squared over 4 pi quantity squared R squared times sine squared theta. I just squared everything. Agreed? Now if I divide that by eta, I'm going to do it right here. This is equal to AR, and it's going to be 1/2 out in front. Now I'm going to take this and divide it by eta. What happens here? If I divide by eta, this gets rid of what?
Eta squared.
One of those etas, yeah. Now it's just going to be eta beta squared, right? Times I naught squared, L squared over 4 pi quantity squared times R squared times sine squared. And that's the power density. No matter how you cut it, that's it. I'm going to show you something that'll hopefully help you. Do you see how this whole thing here is just a constant? For a given length, a given I naught, and a given frequency, isn't that just a constant right there? It's not a function of angle, it's not a function of R. So what I normally do is make what I've circled some constant, call it K. So now I can say that the actual power density, P av here, is equal to just that constant K, whatever that is, all right, divided by, or times sine squared of theta divided by R squared in the AR direction. And that's the power density. You don't have to worry about the constant's value until we do the calculations. Everybody with me on this one? Now what we're going to do is calculate the total power radiated. The way you do an electrical engineering problem or an antenna problem, especially if you're writing code, first you have to find the electric field and the far field, or magnetic field. Then after that, you calculate the power density. And then you have to integrate the power density over a surface far enough away so that there's no near field energy involved. And then we can equate it to something that's important. So now the next step, our next step is this. We're going to take the integral of P av over ds, the surface of a sphere. It's a closed integration. For that, I'm going to go up here. So what I do is this. I go a long ways away, and I put a sphere around there, and I want to calculate all the power radiated from that antenna. Are you with me, everyone? This is very important. So the total power radiated from my antenna, and what should I call this? I don't know what he calls it. How about P rad? Is that what he calls it?
Yep.
All right, so I'm going to go ahead and do it. I'm going to go a long way away in R, and I have this. I have K, right? So it's going to be K. Then it's going to be times sine squared of theta over R squared. Now, and that's in the AR direction, right? And now I need a differential surface in the AR direction. Do you remember what it's dotted into? Do you remember what the differential surface is on a sphere? Anybody? Spherical coordinates? How many remember it's R squared sine theta d phi? And it's in AR direction. Y'all remember that or not?
Yeah.
way they get that is, if you're on a surface of a sphere and you wobble, hold R constant, you wobble this way, well, that's just R d theta. Do you agree with that, class? That's like if you look at a windshield wiper at the tip, if you move through a small angle, d theta, the tip moves the length of the wiper times d theta, doesn't it? Remember that? All right, then you have to get, that's this projection coming down, but then you have to get this projection. Well, you have to take R times the sine of theta, and that's rho, and then you take that d phi. Basically, you get R squared sine theta d phi, and you'll see something like that in his book. Do you see it when he's doing the integral of power over surface? Okay, what page is that on? You're looking.
It's on 445.
All right, you see it, everybody?
Very bottom.
Thank you for bringing the books, I appreciate it. Y'all see it?
Or no, sorry. No, that's not it, sorry.
What page is it? This is the integral of power density.
443.
443?
At the bottom.
What equation? 83, did you say?
8.53.
8.53. All right, now look. This is the differential surface, right? Where is theta varying if you're going over an entire sphere from where to where? I always say North Pole to South Pole, from 0 to...
Pi over 2.
No, that's phi. 0, the North Pole is straight up, South Pole is 180 degrees, or pi down. It goes from 0 to pi. What about the phi integration? That's all the way around the equator. 0 to 2 pi. Now, what do you see happening here to the R squareds? Gone. They're gone, thank God. They go away. What about AR? AR dot AR is 1, thank God. So now I'm left with this, and I'm going to go ahead and just write this down. I have the integral from 0 to 2 pi of k, which I'll take out in front, and the integral from 0 to pi of sine squared, really sine squared theta times sine of theta d phi. Isn't that right, class? It's really sine cubed, but I've done on purpose. I put sine squared there times sine theta. Everybody agree with that? All right, let's do the outer integral first. There's nothing in here that depends on phi, so if I integrate d phi, I get phi, right? Evaluated from 0 to 2 pi is just 2 pi. Do you agree with me? So let me get rid of that. That means here I have 2 pi k. Right? Now, to do this integration, I don't expect you to know all your calculus tricks, but this is one of these things that kind of stays with you. I know that sine squared of theta is equal to 1 minus cosine squared theta, don't I? Right? I'm putting it in for a reason, so this is equal to 2 pi k times the integral, and now it's going to be 1 minus cosine squared theta times sine theta d theta. Still I'm going from 0 to pi, but now you probably see what I'm going to do. I'm going to let u be equal to cosine theta, right? And therefore du is equal to minus sine theta d theta. Do y'all see this in class? What? You didn't like that one? Do you have a different sub?
Oh, no, that's good.
I mean, you follow me on this? This is simply, it's a substitutional thing. So when I do this, if you just watch for a second, I can make this part right here minus du, and I will. This becomes 2 pi k. I'm going to leave the integral without limits for now, so I have 1 minus, and then I have u squared. And then sine theta d theta is minus du, so I'll go ahead and make this a minus sign out here, and du. Now my limits are interesting because my limits go from where to where. If theta is 0, the cosine of theta is 1, so my limits go from 1, right? And then to pi, right? So if if I put down, if theta is pi, u is cosine of pi, which is
-1.
-1, right?
Can't you get rid of the minus sign?
I'm about to. I just wanted to write them up there for complete so everybody sees it. Are you with me? Then, what you can do, as somebody alluded to, it doesn't matter how I do this. I flip this to this, right? And I change the sign, which I'm good at. Right? I just change the limits to get rid of the sign in front. Is everybody with me? Then for this, what does it become? Well, this, let me put it right here. This becomes 2 pi k, right? And then I have, let me do it this way, the integral of 1 du, which is u, right? Evaluated at 1 minus a -1 or 2. Do you agree when I take du and integrate it, the first part, I get u. When I evaluate it at 1, it's 1, minus the quantity, -1 is 1 also, so 1 plus 1 is 2, correct? Now we do the second integration, there's a minus sign. U squared du is u cubed, right, over 3, evaluated from -1 to 1. You'll see why I'm doing it this way in a second. So that's 2 pi k, and now I have 2 minus, well, take a look at this now. What is this going to be over 3? That's 1 cubed, right, minus what? -1, right? I mean, think about this. Well, this is really 1 minus -1 cubed, right? Over 3, isn't it, class? Well, what's -1 cubed? -1. So I have really a +1 there, right? My point is, isn't this really going to be 2/3 right there? That's my old count. You agree with that? Good. So what is this really? Well, this is what? Isn't that 6/3? 2 is 6/3 minus 2/3 is 4/3, isn't it? Do you agree with me? So really I have 8/3 pi times k as my total radiated power. I gotta come back here. I'm gonna go ahead and start this part of the board. We're not done yet, because we gotta put in, k was that, so let me put that in right now. So now I have total power radiated here equals 8 pi over 3 times k, and k was 1/2 times eta, right? It's eta times beta squared times I naught squared times L squared times divided by 4 pi squared quantity squared, and that's what, because that's what k was, so I just put in power radiated. Follow me? Just hang in there. I'm trying to do this quickly, but not just, yakking, nobody catches it. Got it, everyone? Now, that's the total power, and I told you before, you don't get something for nothing. The electrical current that is causing the acceleration of charge is creating and launching photons of energy. And the way that energy really can be, the only way that can happen is if the wire has some resistance, because remember, this is real power being lost, right? This resistance is called a radiation resistance. So this power radiated is really equated to 1/2 I naught squared times R rad. Here, that's the radiation resistance. It's the effective resistance of the wire, or it's the, you might say, it expresses, it's due to the actual power transformation from acceleration of charge to photons, if that makes sense. Because remember, electrical current moving is not photons, but if it's accelerating, it launches photons. It's just the way it is. We call them photons. So that means when I look at this, what is R rad for that one? Well, you all see how I naught appears in both places? Agree, class? So I calculate, I get rid of I naught, and you all see how 1/2 appears in both places. Yeah. So I'm going to do this. I'm just going to get rid of I naught here, and I'm going to get rid of 1/2. And I'm going to write that down. I'm going to show you something. So this is our rad. It's 8 pi over 3 times eta. Now, beta is usually given as 2 pi over lambda. Remember that, 2 pi over lambda. But instead of putting the lambda there, they put it with L. And they put 2 pi squared. And then they put L over lambda squared. Then they put downstairs 4 pi squared. Are you with me? I'm just trying to clean it up. But they usually have L over lambda because the antenna length that you're talking about is in fractions of a lambda. So that would be like 1/10, 0.1, 0.01, if it was 100th. Following? Now we cancel some stuff next. All right. Without spending too much time on this, I have a pi squared here and a pi squared there I'm going to get rid of. Now after that, when I take a look at this, 4 squared is 16. There's an 8 there, right? So I'm going to have a 2 down here. Do you follow me, class? After that, I have 2 squared and a 2 down here. Leaves a 2 upstairs. Do you agree? And I think that will do it. So I have eta pi, or I'm sorry, 2/3. I hope he has this form of them. 2/3 pi times eta times L over lambda squared for antenna resistance in ohms. Does he have this form of the equation?
Yes, but he has eta plugged in. 120 over 125.
You can put it 125 if you want. I usually just leave it as eta naught. All right, but
So he has 80 pi squared, which is what it would be if you plugged in 125.
yeah, all right, but you can do that if you want. You can put this as 80 pi squared, I guess. 80 pi squared, and this is going to be times L over lambda squared.
Yeah.
And that's R rad. Now, that's kind of important to know. That's the radiation resistance, and it's effectively the resistance due to the creation of power that's launched. That's all it is. By the way, that's kind of an interesting concept if you think about it. You're taking charge, Q, and you're accelerating, and you're creating photons that are launched. That's what's really happening. That's what propagating electromagnetic energy is. This is advanced, but if you ever study in graduate school and you get into physics with electromagnetics, there's 2 types of photons. The ones that are launched are real photons. They're little corpuscles of, you'd say, light. It's little smallest things. That light's probably, but the ones that aren't launched, you know, we talked about the electromagnetic energy that is resident with the capacitor when it's charged or with the inductor when steady state currents flow. Those are called virtual photons. And, you know, physics has a way of trying to define things so that they're manageable. Have you heard about subatomic particles? All right, you know, we know about electrons and protons and neutrons. You start breaking them up, you get quarks, charms, right? Keep on breaking, I mean, you get neutrinos, you get a billion little smaller fragments, it seems like. Well, the reason that, I mean, they don't know what they look like, they know how they behave. That's the only thing they can deal with. And light is one of the things that really mystifies people because in some experimental settings, it behaves purely like a wave. And in some, it behaves like a particle. And I don't know how much physics you study, but it is amazing how, even with our best efforts, we can't find one, you might say, one theory that explains the behavior of light for all cases. It really is something that kind of mystifies people, and does me. You know how every wave has to have an ether, they call it back in the old days? Like if you got a rope, you tweak the rope and the thing propagates, it's because the rope's there, right? It's propagating through that media. Sound waves, well, the reason you hear them is because the sound is compression or rarefaction in air, right? The media is air. In a vacuum, you couldn't hear me, right? But light's different. With nothing, light propagates, and it acts like a wave and a particle. And if you know anything about photons, they actually have momentum, which is
have you ever seen, you know, this isn't the experiment, but have you ever seen, they have like a glass ball, and they'll have little pieces of paper at the end of arms, and one side on this little, like almost a paddle wheel, there will be white and the other side black, and you'll see it spinning when the light's on. Has anybody ever seen this? Well, that's not really photons doing it, but photons do cause a pressure. And out there in space, the photons themselves cause things to move. I mean, you can get a momentum change. Does anybody ever, I don't know, you didn't have modern physics, did you? You didn't have quantum or anything? If you ever get a chance, you have quantum?
Yeah.
Well, if you had quantum, you know this thing, probably.
Yeah, the bulb is actually just heat.
It is heat. It is heat for that. But if you could get that in space, in a frictionless situation, then what you would see, if you could just cover one half that sphere, it would rotate just like a water wheel rotates. It would be due to the photons pressure. It's interesting. It always blows me away about things like that, because light doesn't care what you think it should behave like. It behaves its own. If it was just particles, they shouldn't behave like waves. They should bounce around and stuff. They don't. Electrons are even worse. Anyway. Modern physics is not something you can easily understand based on macroscopic observations. All right, so that's the radiation resistance. That now, we're going to get into a few other things. I think in his book, the next thing he does is a loop antenna. Give me 1 second. I just want to mention something about this in his book. He has the small loop antenna on page 445. And he goes ahead and he says, well, IDL, and he gives he basically says it's IS, and he gives some information about that. And then he says, therefore, A is due to that effect, and that's similar to what we did. But he says, this is what I was getting at. On the next page, 446, he says, even if we make certain assumptions that the integral remains quite complicated, the real reason is the integration for this one he's talking about is called an elliptic integral. It's like a special function you probably don't remember because you've never had it. And have you had Bessel functions at all?
Not really, no.
All right, well, Whitworth's right in saying that. I may show you that integration. I may post that. Anyway, for a loop antenna, he gives the solution basically for the electric field on 861. What I'd like to focus on is the dipole antenna. And a dipole antenna, here's what it means. You know, I say these words and I'm so used to them, sometimes I don't define them well. When you have a short antenna like this, all right, when you have something, say it's at the origin, and we have an antenna of length L, and it has a current I naught N. It's assuming I is constant over that length, right? Now, if you just have that by itself, there's going to be accumulation of charge here and here. It has to, right? It's just like the continuity equation or Kirchhoff's laws. Whatever flows in, flows out, or stays there. So charge going up to the top is going to accumulate charge, and then from the bottom become negative charge. And you just have to accept that it's true. Now, when we go ahead and we talk about a true dipole antenna, dipole, whenever they say dipole, it means it has, di is two poles. Well, the poles are the charge centers. You all agree that's plus and that's minus Q if it's operating at instant time, right? Whatever charge is going to be moved comes from the bottom, it's deposited in the top. It has to. Do you agree, class? It's a charge neutral region. Well, that's a dipole, but that is a short dipole because it's small in terms of the wavelength, right? Now, a general dipole is this. If I have some antenna, and we always assume, unless I state otherwise, they're center fed. They're fed right at the center of the antenna.
if this is a length L, and all of a sudden L is not, it's basically unequal to, it's not much less than lambda. It's unequal to that. So it's long. Now, this is the assumption we have to make. We have to assume that the current at this end is 0 and at this end is 0. Let's assume this total length is L. That means from here to here, it's L over 2. This would be L over 2. And from here to here, it would be L over 2, 2. Do you agree with me? Yeah. I'm not going to go off on a tangent and go for another 15 minutes, but I've just got to make this point. Now, the way we do this to calculate the electric field out here a long way, we're assuming this R is so much greater than L that we're 1.5 miles away, so this looks like a dot, basically. Just try to follow me on this one. Here's how we do it. We get the actual differential electric field from a little chunk of current IDL, and then we integrate that value over the length of the actual line. And I'll do that next time. And this gets a little sticky. I want to hit the important points. And I know that vector stuff I did today is probably something you can't really appreciate until you get to higher level courses. But you should see it at least once down here, because it doesn't get it. Thanks for being here. I know that it's, oh yeah. So the question somebody should ask me is, what's the quiz on? All right. Well, it's going to be I'm not going to give it on oblique incidence. I will give it related to, it'll be something related to the problems I give you tonight that deal with short dipole, all right? So that, and I'm not going to make it complicated now. I will give you any bizarre formula. For instance, I'd give you the E field, H field from a short dipole because you've just been introduced to it. And the radiation resistance. But I'll probably ask for calculations. I'm not sure how this quiz is going to shape up. I'll figure it out as I go. All right, guys. Did you at least understand what I was trying to get at today? Because a lot of stuff in Wentworth's book with the vector stuff, I read through that, and he's using a lot of his nomenclature and designations from chapters, earlier chapters, but he doesn't actually specify how some of this stuff comes about. All right, I'll see you. It's not a bad book, though.